Leading and most experienced company in India in the field of near-surface geophysics, including SUE. We have offices in Delhi, Bhopal, Kolkata, Bahrain, and Saudi Arabia, and work experience in more than 14 countries around the world. Now let's start with the topic of this presentation with a small question that if you ask yourself, have you ever been involved in a construction project and encountered utilities that no one knew were there? Well, the fact remains, when I ask this question in my live workshops, 87% say yes and 13% say no. Of course, these 13% are not practitioner. Fact remains that any practicing engineer always has come across a situation where when they were going through a construction of a project, they found the utilities which no one knew about. Now, the reason for this is very simple. This is how the underground infrastructure looks like. It's practically a jungle of utilities down there, going in various directions, in different directions, and that's how it looks like. Now, the footprint of the new construction, repair, or remediation often conflicts with existing infrastructure. So, whenever you're putting something new, it can be a simple piling, it can be putting a new pipe or cable, it can be a bridge foundation. Since you are doing it in the urban area, it is the new construction, repair or remediation is often in conflict with the existing infrastructure, and that's the fact of life. Now, hidden or this buried infrastructure is often detected in the construction phase. So once you start the construction, that's the time you come to know about this infrastructure which is buried there. The problem is when it is detected in that particular phase, your manpower is already there, your machinery is there, so the cost of conflict resolution is very, very high because it practically stops your work for that much of time till the time you are able to do the conflict resolution. And conflict resolution basically would mean either relocating the utility there or changing your plan. Both the options are going to be very expensive. And second is the potential for catastrophic damages. Imagine hitting a gas pipeline, imagine hitting an electrical cable. That's what we are talking about, catastrophic damages. So that is the risk of discovering it at that particular time. So typical design phase, when we talk about it, goes like this, that a person says, I think the gas line is here, but I'm not really sure. It might be in conflict with this proposed piling. And the next guy says, I guess we'll let the contractor worry about that. This makes it extremely difficult to manage the risks that are created by existing underground utilities. This is a fact of life. The design engineer is not responsible for having the information of getting the information of the underground utilities because it is supposed to come from the client. Client gets it from the old records. Contractor does the work as per the design. We have MRI. Now these are the pictures of human body which have been created by using different kind of waves. Now compare these pictures with the pictures here. Now these are the pictures of the subsurface of the earth which have been created using different kind of rays and waves. For example, this is the electrical resistivity imaging showing a shear zone in an otherwise compact bedrock. This has been created using electrical resistivity imaging. These are reinforcement bars in a concrete slab. This is the bottom of the concrete slab. This has been created using GPR. Here are the underground pipes. This has been created using GPR. Here are different layers of the subsurface material up to a particular depth. It's elevation 840 to 800, 810, around 30-35 meters. And it shows the bedrock topography right here. This has been created using seismic refraction tomography. Again, boulders, zone of water accumulation has been created using ERI. So now you compare the images. Here we created the images of the human body using different kind of, here we did not cut open the earth. So geophysics is basically using different principles but in non-destructive way, that is without drilling, without digging, from the surface itself we are finding out what's inside. Of course, our job is much more difficult than medical imaging because everyone knows what a normal human body looks like. These will always be interpreted as joints and not as fractures, but there is nothing called normal earth. So interpretation of geophysical data is much more difficult. Secondly, human body is available for inspection in 360 degree. He goes inside this tunnel. There are transmitter receivers on all the sides, 360 degree. In Earth, we only have one surface to work with. So life is slightly more difficult, but well, that's what it is, and that's where all these methods come in picture. So why use geophysics? I think answer to this question becomes very simple once we have compared it with the medical imaging, that why use X-ray and MRI? Because you just do not want to cut open the body to see what is the problem, where the pain is coming from. You have tools available to see what is happening inside the body. Similarly, use of geophysics, low cost, rapid coverage. You can cover these days with kind of heliborne and airborne geophysics. You can cover hundreds and thousands of kilometers in a day. Continuous information. For example, let's say this is a subsurface. This is a limestone pinnacle here. These are different objects which are buried inside. You have done a hole here. You have done a hole here. You have done a hole here and a here. So what you will ultimately understand is that there is one layer here and there is one limestone layer here. You will miss this, you will miss this, you will miss this cavity, you will miss all these objects because you are not having continuous information in our traditional approach. Whereas once you are using geophysical methods, you get continuous information and none of this is missed. It optimizes test holes. The idea of talking about geophysics is never to say that it eliminates drilling. No, it optimizes drilling. Rather than doing drilling randomly every 50 meters, 100 meters or any particular distance which has been decided, you do a good geophysical campaign and you only drill at very selected locations. So you actually can cut down the drilling from 100 holes to 5 and your information can increase 100-fold because now you are having continuous information. So it minimizes the surprises. As I said, surprise is nothing but something which you could not see, but it's always good for early stage application for better planning and smooth execution of the project. So we'll just start with the few trenchless objective. What do we want to find out in a trenchless project in investigation? First is safe bore path. Okay, so it is desirable to have information on existing utilities like pipes, cables, etc. before finalizing the safe depth and alignment of bore path to ensure safety of equipment, personnel and existing utilities. And geophysical solution for that? The integrated approach of subsurface utility engineering. Now, I'm not going to cover about SUE in this particular lecture. There is a separate lecture for this. But the approach of SUE is what is used to find out where the existing utilities are, and that gives you the safe bore path. The tools which are used are GPR, induction locator, acoustic locator, gas pipeline locators, magnetometers, EM surveying, etc. So there is a sure shot solution for first objective. Second, detecting boulders, cavities, etc. So it is desirable to have information on presence of boulders, cavities and other heterogeneities to prevent deviation of drilling tool and possible loss. And there is a geophysical solution for that, which uses various geophysical tools based on site condition. This has to be chosen carefully. It's not one size fits all. But the tools which are available are GPR. This is an image from GPR. You can see the voids here. Electrical resistivity imaging. This is the image from electrical resistivity imaging, which shows boulders, which shows the zone of water accumulation. MASW, microgravity. This is one image from microgravity. Here is a void here. Seismic tomography. This is the image of seismic tomography where a big void. This was 85 by 60 meters. It was a tunnel project. Depth is around 200 meters. This is 215 meters here. And this was a big void there. So anyway, the idea is to tell that different techniques are available to find out boulders, cavities, etc. Then comes the next objective, determining rock hardness, rock quality and bedrock depth. It is desirable to have information on depth of bedrock, hardness of rock, quality of rock, that is fractured, jointed, etc. to choose the right tool for the trenchless operation. And geophysical solution for that exists, that is seismic refraction. It gives you thickness and depth of various layers of various hardness. You know exactly what is the topography of the bedrock, at what depth the rock is. This is elevation, so you can see around 35 meters here. Electrical resistivity imaging also gives you this information. And MASW, when we talk about shear wave velocity, so this is one MASW, this is REMI actually, refraction microtremor, similar as MASW, except it's passive. It's 100 meters depth. This is all rock interface. This is a bad zone here. So different geophysical solutions for this particular objective. Next objective, subsurface profiles across river crossings. It is desirable to have information on depth of bedrock, hardness of rock, quality of rock, whether it is fractured, jointed, etc. to choose the right tool for trenchless operation across river crossings. And we all know that doing traditional investigation across flowing rivers is very time consuming, very expensive, and it can really delay the project. Geophysical solution for that, again seismic refraction can be done across flowing rivers. Electrical resistivity imaging can be done across flowing rivers. This example is from our project in Karnali, from where in Nepal actually. This is where I did my first work on the flowing river. I think it was way back in 2001 or 2002. And you have beautiful result from this kind of work. This was the river portion, river water, and this yellow line is your bedrock. Rest all are different layers of sediments. So very clearly demarcated bedrock level and different sediment layers in this. So across rivers you can do investigations very quickly, like one river crossing can be done in maximum a day or two, including logistics. So now I'll go very briefly through these techniques. Of course, this is a very short presentation, so I'm not going in great detail. Idea is just to tell you what kind of results you can expect from this. So seismic refraction, as the name suggests, is based on the principle of refraction. So we have a source, it can be a sledgehammer or a weight drop or an explosive, and we start seismic waves from here. They go inside the earth, where there is a change in acoustic impedance, a refraction and reflection will take place at one particular angle. The R will become 90 degrees, so the wave will start traveling along the interface. As per the Snell's law, sin I upon sin R is V1 upon V2. So V2 has to be greater than V1 for that to happen. R will become 90 degree and this wave will start traveling along this interface. As per Huygens principle, the secondary waves will be emitted and recorded at the geophones. Geophones are put in line like this. This is how the geophones are put on the ground. And this way the data is recorded. Geophone is nothing but geophone, that is a phone listening device for the earth. This data is recorded on the geophone. I'm not going in detail of all this. Ultimately, this is what you get. This is depth. So 0 to 30 meters. So this 30-meter depth you are getting. This is your top surface. Now this is your first interface. Here this is the overburden. Okay. Then comes the weathered rock. And then this is a second interface and this is your bedrock. So this way, very quickly, when I say very quickly, one seismic refraction profile to give you a depth of 30 meters takes around 2 to 3 hours of time. And this is how you get a complete topography of what is expected there. Another example of greater depth, 880 to around 800, so 80 meters depth. It was for a hydropower project. Again you can see rock interface clearly. Here. This is how the model looks like. Again, it's 1080 to 1050, 30 meters of depth. This is a distance around 115 meters. You are able to see how the rock is behaving. Now, seismic refraction was giving you more flat interfaces. Seismic refraction tomography is an improvement on that, where you are able to see better profile of your rock. And this is a wonderful example of use of seismic refraction tomography, where there is a shear zone here. You can see very small. It's around 8 to 10 meters. And this has been beautifully picked up using seismic refraction tomography. Now, any amount of drilling or any frequency of drilling will not give you these kind of shear zones unless you go for this kind of continuous method of investigation. Interpreted results look like this. So for example, this is elevation, again 760 to 700 of 60 meters of elevation here. So this is top 400, that is dry silt, sand and gravel. This is based on the velocity, of course. And then moist silt, sand and gravel. Then there is a pocket here which is saturated silt, sand and gravel. Here it is weathered or fractured bedrock because it's 3100 meter per second. And then here is your competent bedrock. So you know exactly at what location, this is distance, at what location, at what depth you are having your bedrock, and where you are having a fracture zone or a weathered zone or a bad zone. So once you are going with your trenchless operation, you know exactly what you are going to meet as you are going from one end to the other. So this is doing job with eyes open. Of course, for people who are more conversant with the geotechnical terminology, there is a Barton scale which correlates VP with your traditional QE scale or RQD. And so applications are bedrock profile, rock quality and depth, thickness of overburden, fracture and weak zones, topography of groundwater, repairability assessment in mines, slope stability studies, pipeline route studies. A wonderful technique to find out the hardness of the strata. The second technique I'm going to quickly talk about is electrical resistivity imaging. Just like in medical imaging, we have X-rays and MRI and CT scan, depending on what you are looking for inside the body. Similarly, in terms of geophysics, when we are looking at strength of the strata, we are going for, let's say, seismic refraction. If we are looking for conductivity of the strata to find out, for example, water zones, we go for electrical resistivity imaging. So here, instead of geophone, we are putting electrodes along the ground. So these are electrodes along the ground. We conduct the investigation. These days it's very fast. Imaging systems are available. And at the end of it, you have the resistivity distribution of the subsurface. So this is the elevation again. And here, for example, this was done across a known drift location. So this is a drift location here. These are, different for study of finding out water lenses or fracture zones. Cavity detection. So this is again a cavity here. Depth can be as high as 500 meters. So this is one investigation which we have done where 500 meters of depth was investigated using ERI. As I said, it can detect boulders, zone of water accumulation, etc. This is detection of a sewer pipe, underground sewer pipe. It can be done across flowing rivers. So this is one of the major applications for trenchless operation. Very quick investigation across rivers. This was from Karnali. This was the river portion, and this was the expected compact rock occurrence, which was interpreted by gradient of resistivity. This, of course, was cross-checked afterwards with the drilling on the location suggested by us. Another river crossing. This was in India and very accurately depicted the bedrock surface. This was a shear zone in otherwise good bedrock. At this location, in fact, they had done some, more than 17 or 19 drill holes. They found rock. This yellow line was a rock, but this shear zone was sitting right across this, which was missed in the drilling. This also can be done to find out condition behind your tunnel. For example, there is some seepage from this tunnel and you want to see where exactly the seepage is coming from. You can do it across this. This is a preparation by drilling holes to put the electrodes. And look at this beautiful example. So seepage was actually coming out from here in the tunnel roof. Generally, you will try to drill here and grout. This is a very, very good massive strata. No grout will go here. Bad zone was actually here and the seepage was taking this path like this. So this gives you eyes before you start the rehabilitation, that where exactly is your bad zone. Next method quickly I will cover is seismic tomography. Now seismic tomography becomes very important because sometimes you are working in area where, for example, your bore path is going under buildings. Now you do not have any access there, you cannot do any drilling, but if you can do two holes on either side, anything can be on top here. It can be a house, it can be a building. If you can do two holes on the either side, everything in between can be mapped using seismic tomography. So it's like CAT scanning. It provides piecewise information of the subsurface condition, and it's high resolution tomography. What we record is travel time and amplitude. So what we do is there is one source hole. So this is a source hole, this is a receiver hole. We send a lot of these waves from source to receiver, and ultimately after inversion you get detailed information of what's happening between the two holes. Very detailed information. I'll show you examples like this. So these were the holes, 5 holes only. Now rather than interpolating between them, you do tomography, and now this fault zone was detected between these two holes, which obviously cannot be detected unless you have this kind of a method. Again, these holes and tomography between them. So it's very, very high resolution. This is something which we did for cavity detection. It was done in Bhutan. You can see a cavity here and the extension of cavities like this. This was pretty deep, around 235 meters. And this is the example which I discussed earlier, 85 by 65 meters, and this was a huge cavity which was in that particular location. Refraction microtremor or MASW is another important method. They both are based on Rayleigh wave dispersion curves, and they give you the VS profile of the subsurface, which are used for earthquake site response, liquefaction analysis, soil compaction control, etc. And they also find buried cultural features like dumps and piers. MASW is very regularly used to find out underground cavities, and these methods are used for mapping the subsurface and estimating the strength of the subsurface materials. This is the kind of result. This is from Bremy, up to 100 meters here. This is the rock interface, and this is the above rock. This was a weak zone here, and this shear wave velocity. So this is the shear wave velocity. You can see up to around 36 meters. It is the velocity 100 meters to 1180 meters. You know what different layers are there. So this is top overburden, the next layer, and the final hard rock layer here. You can of course then take these maps and convert them into site classification. So these are all site classifications. Then N value distribution, allowable bearing capacity, shear modulus or modulus of rigidity, but these are all based on empirical relationship. What you are measuring is shear wave velocity, VS. Next is subsurface utility engineering, SUE. As I said, underground detection of underground utilities is very important. SUE is a very vast subject. There is a separate lecture on that. Those interested may please access that lecture. I'm not going to cover this in detail, but this is basically a procedure to detect and map underground utilities. Here the emphasis is to give a quality level to each utility which is put on a map. That is, once you look at the map, you know how much you can trust that map. That is the basis of the entire SUE operation. There is quality level D, C, B, A, which obviously quality level D is the least reliable information and A is the highest, the most reliable information. The ground penetrating radar is another method which is a very important method for various applications. It is working on the principle of electromagnetic reflection. So you are sending an EM impulse into the ground. It is getting reflected from wherever there is a change in dielectric constant and being captured at the receiver. So you have one impulse as A scan, and once you put number of scans together, it becomes a B scan, and if you do the complete thing in 3D and take a slice out, it becomes a C scan. This is the basic principle, just to demonstrate that a person is moving the GPR antenna from one end to the other. It's a, let's say it's a pipe here. So once it is at 45 degrees, it will start giving the reflection like this, and ultimately a hyperbola is created. So that's how the underground utilities or cylindrical or spherical objects show what we call hyperbolas. The depth of investigation or depth of penetration depends a lot on the type of material. That's why GPR is not something which can be used everywhere in the world with the same effectiveness. It depends on the material. So if the material is very conductive, GPR is almost useless. If material is very resistive, GPR will have great depth of penetration. So as you can see, seawater, almost no depth of penetration. As we are going from very conductive to very resistive, you are having very high depth of penetration. For underground utilities, 5 to 6 meters is what we look for, and that is what appropriate frequency of GPR will provide. So penetration depth and ability to locate targets at any depth is strongly dependent upon local soil properties. Depth of penetration is also limited by presence of highly conductive material. So highly conductive soils, as I said, can render this method completely ineffective. There must be a sufficient electrical contrast between the target and host material to see a reflection. Of course, you can detect both metallic and non-metallic, but there should be a contrast. And very important is the rule of thumb that GPR target with a diameter of approximately 10% of target depth. That is a target with a diameter of 1 inch for every foot of penetration. That means that a 2-inch cable or pipe can be detected up to 2 feet of depth, but the same if it goes to 4 feet, it will not be detected. There are a lot of details in this. I cannot really get into that, but it just depicts. For example, this will be detected here, but the same thing, it goes much deeper, it will not be detected. So to be detected at great depths, the size should be increasing. There are various equipment available. This is a Mala equipment which comes in a single frequency and dual frequency. These days array type equipment also are coming, which have number of antennas built in, which can make the whole thing very fast. It is done generally in a grid fashion, and these days 3D processing is possible to make the complete map in 3 dimensions. These are great capabilities and make the work much more effective and powerful. It is used a lot for archaeological investigation also. It also can be used for cavity detection. So this is a cavity at 18 meters using GPR. This is 7 meters, 18 meters, 7 meters. Results of the entire geophysical investigations can be presented even like this. This is a 3-dimensional result. This was for cavity detection. This 60 meter by 300 meter block, 60 meter depth. All this blue what you see is water level. There was a cavity which was suspected because at the time of drilling, that drilling rod had just completely gone down suddenly for 60 centimeter. They wanted to know what is the extent and size of the cavity. So this investigation was done using ERI, and this is the cavity which you see. This blue one is going from one end to the other, and this was the cavity which was detected beautifully using ERI. This is a signature of cavity here. This is all water table, this blue one. So results can be presented in very simple ways to understand. There are failures and disappointments, of course. Wrong tool selection is one of the reasons for that. You choose a wrong tool for a wrong application. For example, there is a soft zone under a hard layer and you choose seismic refraction. It will not work. You try to use electrical resistivity imaging in situations where there is a highly conductive layer which does not allow the penetration of current further down. ERI will not work. You try to use GPR in a highly conductive material like saturated clays. It will not work. So wrong tool selection. Method lacking desired resolution. If your method is such that it cannot resolve a very small target at great depths, well, it won't work. Geology ignored. Calibration of the equipment ignored. Only single tool used. I always recommend that for solving any problem you should use at least a combination of 2 tools, generally more, but that's the minimum. Or wrong data processing and interpretation. That completely depends on the experience of the professional who is doing the job. With this, I come to conclusion of this particular session, and I'll take questions after this. I would really like to thank you for your attention. Here is my email ID. You please feel free to write to me for any of your queries. Thank you very much.